Okay, in the last lecture we talked about how to use implicit method to solve heat equation, right? Let me quickly refresh your memory. So we were using implicit methods. Okay. And specifically we are solving heat equation, right? So we're continuing to solve heat equation. Okay. And we basically solve this equation implicitly, which means simply I would say Ti plus 1 minus Ti divided by delta T is equal to or Eti is equal to d times Ti minus 1 minus 2Ti plus, actually we did it other way around, Ti plus 1 Ti minus 1. Remember, this is all at L plus 1, or since you use this PTI notation, this is all at the new time levels, the current time levels, okay? And then we reduce this, we went through mathematics and reduced this as A Ti minus 1 plus B Ti plus C Ti plus 1 is equal to Pti, okay? And we define this as B and C. Okay? Now from this we could actually write a matrix equation, and we talked about it, how to develop a matrix equation. Okay? Now, in general, when we build matrix problem, this equation actually applies to all internal nodes. Okay? This equation will apply to all internal nodes, which means if we had in our problem we had a 6-node system. So this was a 1 and a 6. So it'll apply to 2, 3, 4, and 5. Okay, so it's not a problem at all. 2, 3, 4, 5. All internal. These are called internal nodes. Okay, all internal nodes. I can blindly assemble this matrix. Okay, because remember I also know that value of A, B, C, D. A turned out to be minus lambda. B is equal to 1 plus 2 lambda. C is equal to minus lambda. D is equal to Pti, right? So for all the internal nodes, I can simply write A1, A2 must be equal to minus lambda, A3 must also be equal to, so on. Okay? Similarly, I can write C2 is equal to, or B2, sorry. B2 is equal to 1 plus 2 lambda. Assuming I calculate lambda, B3, I can calculate that. Similarly, I can write C2 and write there, and similarly B2. Okay? So all the internal nodes I can right away assemble these matrices. Okay, but for the boundaries have a very special property. Okay, so there are two types of boundary conditions. Okay, in this particular case, what we are dealing with is what we call a fixed temperature boundary condition. Okay, so I equal to 1. DC1 says the temperature is fixed. Okay, so this is called a constant temperature boundary condition. So under constant temperature boundary conditions, for all constant systems, the way in which we're going to write the program, or the way in which we have organized the program, is very simple. It simply turns out, remember the very first row in that matrix, if you go back and look into your notes, it basically had 1 here and 0 everywhere else. Okay? So this is my B. This is my diagonal, so it should be B. Okay. So it turns out for constant boundary condition, my left BC, A1 will become 0, B1 will become 1, C1 will become 0, and D1 will be equal to my BC1. Okay, whatever the temperature, in this case it's 100. Okay. Similarly, my other extreme is also BC2 is also a constant temperature boundary condition. This is my BC2. Okay. So AN, which is equal to A6 in this case, will be also 0. Okay, and similarly BN will be 1, CN will be 0, and BN will be equal to BC2, which is equal to 100 degrees centigrade. Okay? So this is how you deal with constant temperature boundary condition or constant head boundary condition. Anytime something is constant, you simply blindly set all these first entries to 0, A0, C0, and D is the boundary condition, and B will become 1. Okay. Similarly, at the other node, it becomes 0, and then D becomes the second boundary condition. Okay. That's how you deal with constant temperature boundary condition. Okay. Now, there are other conditions other than the constant temperature boundary condition. For example, let's consider a system, the same 6-node system. Okay, so let's say that I have the same 6-node system. Okay. This is 1, 2, 3, 4, 5, 6. Okay, it's the same 6-node system with temperature T equal to 100 degrees centigrade. Okay. Now, or some constant, I don't know whatever the constant it is. Okay, and instead of fixing this node at some fixed temperature, let's say I'm going to insulate it. I'm going to seal this. I'm going to put an insulator around here so heat cannot go out. Okay, so no, which is also called no flux BC. This is a second type of BC condition, boundary condition. Okay. Now, mathematically, I can write this expression as at x equal to L, dt by dx equal to 0. Why? Because heat flux is what? We remember we talked about heat flux. Heat flux is nothing but, just like Darcy's flux, it's nothing but K times K dt by dx. It's conductivity of the material times first. Now, if that becomes 0, I can get dt by dx equal to 0. Okay? And this is a no flow BC, no flux BC. Okay? So what happens in this case? Let's assume in this case also initial condition T equal to 0. So the rod is at temperature 0, you're just heating one side. The final condition will be obviously the rod will become everywhere 100 degrees centigrade. Okay, it will just keep heating up. Okay, and that's what we want to eventually see. Okay, because there is no temperature is fixed. This is a sealed boundary condition. Okay? So to handle this boundary condition, mathematically we got to do some go through a little bit of a trick. Okay, so now you remember when we write these equations, we write this general equation for every node. So we know at I equal to 6, the sixth node, there are two things which are true. Okay. The general equation should be applicable. I can write a general equation which is A Ti minus 1 plus B Ti plus C Ti plus 1 equal to Pti, okay, or D. Okay. Reminding you, D. Okay. This is applicable at I equal to 6. Okay. In addition, we also know dt by dx, a mathematical condition which is dt by dx equal to 0. Okay? So what we're going to do is we're going to treat this last node as separately. Okay? So here's my last node. This is my last node which is sealed now. Okay? And this is the node before that. And we're going to assume we're going to basically treat this node such a way that so this is my ith node, I equal to 6. Okay? And this is my I minus 1th node. And I'm going to assume an hypothetical node which is I plus 1th node, okay? Which will be actually 7. Okay? So, if I write this equation, I can write equation here. I can write A times temperature at 5 plus B times temperature at 6 plus C times temperature at 7, this hypothetical node, is equal to P times temperature at 6. Okay, that's the condition. Okay, I can write that. Okay, now that's from the general expression. Okay, so now from this equation, I'm going to do a generic expression, which is I can do a simple central finite difference approximation and write that can be that's nothing but Pi plus 1 minus Pi minus 1 divided by 2 delta x equal to 0. This is the central. I'm simply writing a central finite difference between these two nodes. Okay, so I can write that. Okay. From this, what I get is, from this I can get Ti plus 1 must be equal to Pi minus 1. Okay. This again implies, T5 must be equal to T7. Okay. This is coming from this condition. Okay. So now I can modify this again. Okay. So I can modify this equation and write, okay, A times T5 plus B times T6. Instead of T7, I'm going to write C times T5 equal to T6. So I got rid of this magic node or imaginary node. Okay. And once I have that, I can now pull things together and write A plus C times T5 plus B times T6 is equal to T6. Okay. So my last equation turned out to be my boundary condition. This can be implemented directly as a boundary condition. So my last equation, or the nth equation, turns out to be something like this. It will be 0, 0, 0, 0, and A plus C here times B equal to PTR. Okay. So what happens is, so when I actually define the variables an, so remember this is my B, right? So an will be nothing but A plus C actually. Okay. So so remember A is minus lambda and C is also minus lambda. So it's a special equation. Okay. And B is exactly same as B. Okay. Bn is just B, whatever we define. And di is equal to PTR, P7 basically, PTR 6. Okay. Or D not di, dn, or n is equal to 6 actually, n will be 6. Okay. So if we use this boundary condition, this will basically represent a no flow boundary condition or a no flux boundary condition. So this is how we model the no flux boundary condition. Okay. So one of the homework problems involves using no flux boundary conditions. So the only difference with the no flux boundary condition is you use the same code, except at very last node, when n is equal to 6, you make this modification. You make this minor modification, and that will modifications to an, dn, cn, and dn. Okay. If you make these modifications to the very last node, and then solve the problem as you solve as an implicit solution, that will simulate the no flux boundary condition. Okay, and that's one of your homework problem, and I want you to finish it using this ideas. Thank you.